All right, chemistry, let's take a look at our video lecture for the combined section of chapter 8, sections 2 and 3. So what we're going to do here for section 2, we're going to define and give general equations for synthesis, decomposition, single displacement, and double displacement reactions. So we have to not only define each of these types of reactions, we also have to give general equations, so like archetype of equations using variables like A, B, C, or D, X, Y, Z, not necessarily real life examples. And then secondly, classify a reaction as synthesis, decomposition, single displacement, double displacement, or a combustion reaction. In this case, you are going to have to look at real life examples and identify them as one of these 5 types of reactions. You're also going to have to list 3 kinds of synthesis reaction and 6 kinds of decomposition reaction. And again, we'll go over those in the notes. List 4 kinds of single displacement reactions and 3 kinds of double displacement reactions. Again, we'll go over those in the notes. And lastly, predict the products of simple reactions given the reactants. All right, I know it sounds like a lot, so let's get started. So there are several ways to classify reactions. The classification scheme described in this section provides an introduction to 5 basic types of reactions. There are more than this, but these are the 5 basic ones that we are going to introduce here. Like we've already mentioned in the objectives, it's synthesis, decomposition, single displacement, double displacement, and combustion. In a synthesis reaction, also known as a composition reaction, if you guys remember, one of the things we're going to talk about is a decomposition. So the opposite of decomposition would be composition. All right, so in a synthesis reaction, also known as a composition reaction, 2 or more substances combine to form a new compound. This type of reaction is represented by the following general equation. So this is going to help you satisfy objective 1 for this section. A plus X react to yield AX. Right? 2 things coming together to form one new thing. One trick is there are 2 reactants, 1 product. Not necessarily the numbers 2 and 1. It's the fact that there are more reactants than there are products. Okay, that's the synthesis reaction. So A and X here, they can be either elements or compounds, doesn't matter. But AX, the product, is for sure a compound.
Carbon dioxide and water can react to form sugar and oxygen. This is an example of a synthesis reaction. 2 substances have combined to form a new compound, sugar.
Continuing on with synthesis reactions. You're going to have to identify, remember, 3 different types of synthesis reactions. Well, we have reactions of elements with sulfur and oxygen here. One simple type of synthesis reaction is a combination of an element with oxygen to produce an oxide. You've heard that before. In fact, last chapter we were talking about different oxides of elements. That just means it's bonded with oxygen. Almost all metals will react with oxygen to form an oxide. For example, if we react magnesium with oxygen, we get magnesium oxide. Notice here that this is a balanced chemical equation, 2 in front of the magnesium, 2 in front of the magnesium oxide. Any group 2 elements will react in a similar manner, forming oxides with the formula MO, where M represents the metal, right? Group 2, that means that they're going to have 2 valence electrons, so when they ionize, they're going to form a +2. That means you only need 1 oxygen in order to balance that out, so that's why you only need 1 of the metal, 1 of the oxygen. We can also have a group 1 metals form oxides. But it's going to have a different formula because remember, group 1 metals are going to have 1 valence electron, so they're only going to form a +1 as an ion. With that oxygen still being a -2, we're going to have 2 of the metals to balance out the oxygen. So we're going to have the general formula M2O. So an example is going to be lithium oxide. Lithium oxide is going to have the formula LiO, right? There's only 1 oxygen. The group 1 and group 2 elements react similarly with sulfur because sulfur is in the same group as oxygen. It's going to want to gain 2 valence electrons, so it's going to form a -2 charge when it does ionize. But instead of calling it an oxide, when you're bonding with sulfur, it's called a sulfide, right? Because that's the name of the anion that sulfur forms. And so we're going to have formulas M2S or MS respectively. For example, we have rubidium reacting with sulfur right here, and then we have barium reacting with sulfur right here. Notice we need twice as much rubidium as we would need barium to react with 8 sulfurs because we need to balance out the charges there. Nonmetals also go synthesis reactions with oxygen to form oxides. So we had metals with oxygen, now we have nonmetals with oxygen. We can have sulfur, for example, react with oxygen to form sulfur dioxide, right? Remember that naming system, dioxide, referring to 2 oxygens. Another example would be hydrogen, because remember, hydrogen, even though it's in main group 1, is a nonmetal. Hydrogen reacts with oxygen to form dihydrogen monoxide, aka water. Again, because we're not balancing charges here, we're simply sharing electrons. There's no way to balance charges to know what the formula is, so we're going to have to use the prefix system here of nomenclature. Specifically, within those nonmetals, we have halogens reacting with metals. Okay, so we've had metals reacting with oxygen and sulfur. We've had nonmetals reacting with oxygen, and now we're going to have halogens reacting with metals as one of our synthesis reactions. Most metals react with the group 17 elements, the halogens, to form either ionic or covalent compounds. Group 1 metals react with halogens to form ionic compounds with the formula MX. All right, group 1, +1 charges, halogens are all going to be -1, so you just need 1 of each. Where in this case, the M represents the metal, the X represents the halogen. With the example here, 2 sodiums reacting with a chlorine molecule to form 2 sodium chlorides. Let's look at that with the group 2. Group 2 metals, again, are going to form +2, so we're going to need 2 halogens to balance that out for this ionic compound. So my formula here is going to be MX2, with my example being magnesium reacting with a fluorine molecule to make magnesium fluoride. Fluorine here is so reactive that it's going to combine with almost all metals all the time. Now here's a word that we are going to use in more depth in section 3. But active, right, high activity, active metals are highly reactive. So active is the same thing as reactive. Oxides of active metals react with water to produce metal hydroxides. So if we have a metal oxide, right, a metal bonded with oxygen, and it reacts with water, we can get a metal hydroxide. And hopefully you remember from your polyatomic ion sheet that hydroxide is OH with a -1 charge. It's a polyatomic ion. So if we have calcium oxide, again CaO, and we react it with water, we can get a calcium hydroxide. So we have the calcium atom, right, ion I should say, +2 charge. We would need 2 hydroxides to balance out that +2 charge. So our calcium hydroxide would be CaOH2. Many oxides of nonmetals in the upper right portion, right? Upper right, so the nonmetals, the highly electronegative elements, react with water to produce oxyacids. Remember, those are acids that have oxygen in them. So if we react sulfur dioxide, right? Sulfur being in the top right, right, upper right-hand portion of the periodic table. If it reacts with water, it's going to form, well, that's sulfurous acid, SO3. Sulfite becomes sulfurous. Certain metal oxides and nonmetal oxides will react with one another to form a salt. Okay? A salt is simply an anion and a cation. We use the word salt specifically for an ionic compound that is a result of a synthesis reaction. So we have calcium oxide and sulfur dioxide reacting to form calcium sulfite, right? That calcium sulfite, because it was formed through this reaction, is going to be considered a salt. On to decomposition reactions, and I will remind you just last thing, 2 reactants become 1 product. Okay, we have more reactants, we have fewer products. That's going to be your simple identification, your simple red flag to ID that synthesis reaction. Decomposition is actually going to be the opposite of that. In a decomposition reaction, a single compound undergoes a reaction that produces 2 or more simpler substances. Decomposition reactions are, in fact, the opposites of synthesis reactions. They are represented by the following general equation: AX reacting to form A and X. Notice we have 1 reactant, we have 2 products, right? We have more products than we have reactants, right? That's your red flag for a decomposition reaction. So here, AX is the compound. A and X can either be elements or compounds. Now, there are a couple of different ways we can accomplish decomposition. Most of the time, it's going to involve the addition of energy in the form of either heat or electricity. And so when we have a decomposition reaction occur because an electric current is applied, we call that electrolysis. And we're going to show that that's taking place by just writing the word electricity over the reaction arrow. So we can actually decompose water into some pretty reactive gases by applying electricity to it. Now, if we have an oxide of a less active metal, which are located in the lower corner of the periodic table, we can have them decompose into their component elements by heating them. So here we have mercury oxide. We can decompose it into mercury and oxygen by applying heat. Again, this little delta means heated. So decompositions usually require either an electric current or heat.
Electrolysis is the use of an electric current to cause an oxidation-reduction reaction. Electric current is the passage of electrons. Because oxidation is the loss of electrons and reduction is the gain of electrons, the passage of electric current through a solution causes these reactions. For example, when current is applied to water, the hydrogen in the water is reduced to elemental hydrogen, and the oxygen is oxidized to elemental oxygen. Because 2 moles of hydrogen are formed for every mole of oxygen, twice as much gas is formed in one tube as in the other. When the electricity is shut off, the reaction stops. Electrolysis is also used in electroplating.
All right, so we also have a couple of different types of decomposition that we want to look at, specific examples. So we're going to have a composition usually as a result of adding heat or electricity, but we can decompose different types of substances and get a pretty generic, pretty normal set of products. So we can have the decomposition of metal carbonates, right? So metal, calcium, that's a metal. CO3 is a carbonate. It's a metal carbonate. By adding heat, we can decompose it into calcium oxide and CO2. We can decompose a metal hydroxide, right? Here's a metal, calcium, it's the metal. And then hydroxide, we can heat it and decompose it into calcium oxide and water. We can also decompose a metal chlorate, right? ClO3, that's a chlorate. Here's my metal, potassium is the metal. I can heat it in the presence of a catalyst to form potassium chloride and oxygen. So here, if it's a metal carbonate, it's going to decompose into a particular product and carbon dioxide. Decomposing a metal hydroxide, you're going to produce water also. Decomposition of a chlorate, you're going to have pure oxygen. So that's something to keep an eye out for. We can also decompose acids. Certain acids decompose into non-metal oxides and water. Okay, non-metal oxide, something that's not a metal. For example, carbonic acid is very unstable and decomposes readily at room temperature to produce carbon dioxide, right? Carbon's not a metal, so that's a non-metal oxide and water. And we're going to pick up with single displacement reactions next time we meet. The last thing I want to just remind you of for this decomposition, notice that they are the opposite of synthesis reactions. As I go back to this slide, notice that these types of reactions, if you simply go the other way, they are the synthesis reactions that we identified in the synthesis portion of these exact same notes. And then the simple red flag to let you know that this is decomposition. Notice there's only one thing as a reactant, two things as a product. That's fewer things becoming more things. That's your red flag that you are looking at a decomposition reaction. All right, chemistry, I will see you next period.